All right, let's do this. So we're going to finish off our conjugated diene chapter by talking about one more set of reactions here, one more class of reactions, what are called electrophilic addition reactions. You would have talked about these with regard to just regular old alkenes in the first semester of the course. Now we're going to kind of build off them with our conjugated dienes. Before we jump in, we're going to throw down some vocab that we're going to be using a lot in this course. Nucleophile and electrophile. All right, these are roles that are played in an organic chemistry reaction. A lot of our reactions in organic chemistry, they occur because one species has a lot of electrons and it's going to react with something that doesn't have a lot of electrons. All right, our nucleophile, what does that word suffix phile mean? Lover. So our nucleophile is the species that is electron rich. And because it's electron rich, it loves those positively charged nuclei. All right, our electrophile is relatively electron poor. All right, and because it's electron poor, it loves those negatively charged electrons. Okay, and chemical reactions occur because our nucleophiles, quote unquote, attack electrophiles. The species that is electron rich, so you want to have synonymous in your mind, nucleophile and electron rich, will attack the species, the electrophile, which is electron poor. All right, so let's look at these electrophilic addition reactions of just regular old alkenes, and then we'll graduate to our conjugated dienes. All right, so if we take an alkene, we can do an electrophilic addition reaction by combining it with a hydrohalogen like HCl. Okay, this is called an addition reaction because what we're going to do is add that HCl to our organic molecule. We're going to add to one side of that carbon-carbon double bond here. One of those carbons gets the hydrogen, the other carbon gets that chlorine. So we've added that HCl to our molecule here. All right, so this is our electrophilic addition reaction. Okay. And this is a reaction where not only did you learn, your substrate reactant product combination, but you actually got the mechanism for this reaction as well. All right, so if we're going to do our mechanism, first of all, one of the ways that you get really good in organic chemistry is by developing a sort of X-ray vision or electron density kind of vision. Because again, all of our reactions, we can understand them as something electron rich reacting or attacking something that's electron poor. So when I look at this alkene here, what I see is this carbon-carbon double bond is glowing red hot with a lot of electron density. All right? Remember we talked about these carbon-carbon double bonds, these pi bonds, and what makes them so special compared to other single bonds is that that electron density is sitting out there in the open above and below that molecule. All right? So it's not tucked away between those two carbon atoms. It's nice and accessible on the top of that molecule. So that carbon-carbon double bond is glowing red hot. All right? And if I look at this molecule here, where's the electron density in HCl sitting? On that chlorine. Chlorine's much more electronegative. So it's pulling all that electron density away from that hydrogen, leaving that hydrogen relatively electron deficient, electron poor. right? So in my reaction here, again, I'm kind of imagining that this double bond is glowing red hot with this electron density, and my hydrogen's really cold here. It doesn't have a lot of electron density. And so what happens is that nucleophile attacks that electrophile, and that chlorine will accept that pair of electrons, so that hydrogen doesn't break its octet rule. Okay, I'm going to call these carbon 1 and 2 here, so that we can make a point. We're now going to draw our intermediate for this reaction. First of all, we have that chloride ion. That's that bond breaking arrow. So that bonding pair of electrons got turned into a lone pair on that chloride ion. All right, and what about that second arrow? Was that bond breaking, bond formation, or both? So we got a bond forming, but we're also going to break this carbon-carbon double bond as well. So that was our both category. It's both a bond breaking and a bond formation arrow. Now, importantly, the carbon that gets my hydrogen is very specifically going to be carbon 1, because what forms on carbon 2 in my intermediate? A positive charge, all right? So first of all, how can we see that a carbocation formed? Well, first of all, that second carbon got that pair of electrons taken away from it, so that's what leaves it with its incomplete octet. We can also just convince ourselves based on our conservation of net charge. Everything up here is neutral. Everything in this second step better be neutral as well. So if I have a negatively charged chloride ion that forms, I'm going to also have to form a positively charged carbocation. All right, so then finish the mechanism here. Put in your missing electron pushing arrows at this second step. All right, again, we got to be good at these electron pushing arrows here, both following them as well as drawing those in. I teach the first semester of this course as well, and they've already got these electron pushing arrows down. We already had our exam on that, right? So it's something that at this point we got to know going forward. We're going to use them over and over and over again, okay? So I need that bond formation arrow in order to get my product here. Cool. And this carbocation formed specifically on this second carbon, what we call the regioselectivity of this reaction, because this secondary carbon here forms a much more stable carbocation than this first carbon. It's what they called a Markovnikov reaction. All right, but importantly, it stems from our carbocation stability. All right, if we're going to rank carbocations from least stable to most stable, we're going to see that it depends on how substituted those carbons are. The least stable carbocation you could have, the one that you'll never really see, is a methyl carbocation. All right, they get more stable as you increase the number of carbon neighbors. So the next most stable here, or least stable, would be a primary carbocation, followed by a secondary carbocation. All right, and then lastly, at least from what we've learned in the previous semester, the most stable carbocation we can have is a tertiary carbocation. And I'm going to leave a little bit of room because we're going to learn about one that's even better later here today. Okay? But so the reason why carbon 1 gets the hydrogen is because carbon 2 gets that carbocation, and that carbocation would be more stable forming on that secondary carbon than it would on carbon 1, which is a primary carbon. All right? So by electrophilic addition, this is the reaction that I'm referring to here. Reacting our alkene, where the alkene, specifically that pi bond, plays the role of the nucleophile with a hydrohalogen. First, we have our intermediate, our carbocation intermediate form. We can also sort of see our chloride here is now glowing red hot and attacking that relatively electron deficient carbocation in order to get my alkyl halide product. Cool. All right, so now we're going to look at our electrophilic addition reaction, but we're going to specifically look not at alkenes, but conjugated dienes. Okay, so we're going to take a conjugated diene. We're going to go with the simplest 1,3-butadiene here. We're going to react that again with our hydrohalogen. All right, and that first step is the exact same. We have our pi bond playing the role of the nucleophile, attacking that electron deficient hydrogen. Okay, so everybody take a second and draw me my intermediate here. We're going to see all 4 of these carbons end up being involved in our reactions. So just like we did with our Diels-Alder, I'm going to number them carbons 1 through 4 here, right, about that conjugated diene. So if I go over here as well, which carbon do we think gets the hydrogen in our intermediate? Carbon 1, which means that what's on carbon 2? That carbocation. All right. And so I believe everybody would have gotten this here based on analogy of what we discussed before. And this is correct, but for a reason that's different than what y'all are thinking. It doesn't have to do with the fact that this carbon is a secondary carbon. It has to do with the fact that it's right next door to this carbon-carbon double bond, what we call the allylic position. Because it turns out that in our scheme here, what's even more stable than a tertiary carbon is one that's located right next door to a double bond or a allylic carbocation. All right, that's the most stable carbocation that you can have. Okay, so it actually wouldn't matter whether carbon 2 was more substituted or less substituted. It would always form on carbon 2 because that's the allylic position, because that's the position located right next door to that other carbon-carbon double bond. All right, and then we have our chloride. That electron-rich chloride ion is going to attack that electron-poor carbocation, giving me my electrophilic addition product. Right? So far, just direct analogy to what we did with our regular old alkenes. That second double bond has not come into play at all here, okay? But it turns out that this isn't the only product that we can get. There's a second product that we can get as well. So first of all, going back to this allylic carbocation, what is it that would make an allylic carbocation so stable? Resonance, exactly, right? So charges in general, atoms don't like to have formal charge. One way that we can make it more stable is by spreading that charge out across multiple atoms in what we call resonance. And so exactly, we can stabilize this double bond through resonance. So now if we draw our other resonance contributor, that pi bond is going to have switched places with that positive charge. Okay, so my other resonance contributor here now has the carbon-carbon double bond between carbons 2 and 3. And the carbocation itself has formed on carbon 4. All right, so this is what we would call resonance of that allylic carbocation. Okay, so my chloride ion, just like before, can then react now with that other position, giving us our other possible product. So we have two possible products in this electrophilic addition of conjugated diene. The first, exactly what we would expect based on the reaction of alkenes, and the second one that results as a consequence of the resonance of that allylic carbocation. All right, again, just kind of looking at my numbering. We call this first one the 1,2 adduct, because that addition has taken place on carbons 1 and 2. Our other product that forms as a result of resonance is what we would call the 1,4 adduct, because the hydrogen is added on carbon 1, the chlorine added on carbon 4. All right, you can also note that in your 1,4 adduct, your carbon-carbon double bond has moved places as well, right? As a result of that resonance, it used to be between carbons 3 and 4, and now it's between carbons 2 and 3, all right, as a result of that resonance jump that we saw. Okay, so just to summarize here, we take a conjugated diene. We react it with one of those hydrohalogens. We get two possible products. Our 1,2 adduct and our 1,4 adduct. Cool. So it turns out that we can bias this reaction towards one of these products or the other one by tuning the temperature of our reaction. So it turns out that if we were to carry this reaction out at low temperatures, our 1,2 product would be the major product, and our 1,4 would be the minor product. if instead we increased our temperatures, so low temp, if instead we carried out this reaction at high temperatures, we'd see the reverse. Our minor product would be the 1,2, and our major product, the 1,4 adduct. All right, so why is that? Before we can kind of jump into explaining this particular reaction, let's just review something from all the way back in Chem 1B, free energy diagrams. These are these graphs, these curves that we use to describe chemical reactions in all of chemistry, really. All right, what we're going to do is we have this graph. Our y-axis of this graph is energy, and our x-axis of this graph is what are called reaction coordinates, or reaction progress. Okay. Over here on the left-hand side of our graph, this is our energy of our reactants in our chemical reaction. And on the other side is the energy of our products. All right, and our free energy diagram here is telling us what's happening to our energy as reactants get converted into products. First, you got to put a bunch of energy in order to break chemical bonds, but then you get a bunch of energy back out when those new chemical bonds form. All right, so we get a curve that looks something like this. Okay, so these are these energy diagrams that we use to describe chemical reactions, and there's two important pieces of information that are contained in these free energy diagrams here. The first is the thermodynamics of this reaction. Right? The thermodynamics of a reaction is the difference between the energy of your reactants and products. All right, remember from Chem 1B, in terms of the free energy of a reaction, in terms of the thermodynamics of a reaction, all that matters is where you start and where you end. It doesn't matter how you get there. So if we're looking at this graph here, the only thing that I'm paying attention to when I'm talking about the thermodynamics of the reaction is my reactant energy compared to my product energy. So this gap right here tells me about my thermodynamics of my reaction. All right, my delta G. All right, but there's another important piece of information in this graph here, and that is what happens in the middle. All right, so how we think about our reaction with regard to this little graph here is our reaction starts off as a reactance, right? So we think about it as a little marble on this graph at this reactant energy level. And in order for the reaction to occur, in order for it to get over here to the product side, it has to jump over this barrier in the middle. This barrier in the middle here that this thing has to jump over is what we call the activation energy barrier. A fast reaction has a small activation energy barrier. It's really easy to jump over. A slow reaction has a very large activation energy barrier. It's much harder to jump over. All right? So in addition to the thermodynamics of a reaction, we can also learn about the kinetics of a reaction from this graph. All right, that has to do with the height of this barrier here, which again we call the activation energy. All right, so when we look at one of these graphs, again, we get these two pieces of information. How favorable a reaction is from a thermodynamic standpoint. Remember, low energy is good, so if your products are much lower energy than your reactants, that's a very favorable reaction. A reaction that's equilibrium very much so favors the product side. But we can also learn about the kinetics of the reaction, how high this activation energy barrier is, how hard it is to jump from the reactant side to the product side. All right, so these two pieces of information we can get from this graph here. So going back now to our reaction here, we're going to try to explain why this reaction has this sort of pattern where our major product at low temperatures is the 1,2, but our major product at high temperatures is the 1,4. All right, so we're going to draw a free energy diagram here. Okay, so I'm going to put down this first curve here for my 1,2 adduct. I'm going to do that in blue. And I'll do the 1,4 in a different color. We'll do this one in red. All right, so my reactant energy level, it's right here. And my products are at a lower energy level down here. And we've got our activation energy barrier in the middle. All right, so over here are my reactants, my 1,3-butadiene and HCl. And over here is my product, specifically my 1,2 adduct. All right, great. So we got one curve. Now let's compare that to our other product. I'm going to do this curve here in red for our 1,4 adduct. Okay. So first of all, where am I going to start this red curve here? Am I going to be at the same, lower, higher? Where am I relative to the blue curve? Am I starting out with different reactants? No, I'm starting out with the same 1,3-butadiene and HCl, right? So everything's going to start in the exact same place, okay? But when I look on the other side, my product side, what we're going to see is that our 1,4 adduct is actually lower energy than our 1,2. All right, so why would that be? Let's look at these two products closely. What is it about this 1,4 adduct that makes it lower energy than our 1,2 adduct? Right? Another way of saying that is, why is this molecule more stable than this molecule? Not sterics. The pi bond, and what about the pi bond specifically? So they're both, this one doesn't have stereochemistry, so yes, this one has that more favorable stereochemistry, but what's even more important than stereochemistry on our list of factors? So allylic, they're both chlorines are kind of on that allylic carbon, so there's no allylic carbocation in either one of these. What's that other factor? Tertiary? So yeah, so not tertiary, but we sort of the same way of saying it, our substitution, right? Which one of these double bonds is more substituted? This one would be what? Mono, di, tri, tetra. Mono substituted, and what about this one? Di substituted, right? So this one's more stable, aka a lower energy, because it's the more substituted alkene. All right, so our 1,4 adduct here, lower energy, let's say more stable, because it's more substituted. All right. However, what goes on in the middle of this graph is also different between these two reactions. Remember that in order for this 1,4 adduct to form, we had to have this resonance jump that occurred. Our double bond traded positions with that carbocation. Not only that, but what turns out to be an even more important factor is this chloride right here. When this chloride ion forms, it's all the way at the other end of this molecule near the hydrogen. In order to get to the other side, it's got to migrate over there using thermal energy. So because of that, the height of my activation energy barrier is greater for that red reaction than for the blue. That's terrible. Okay, so again, if we look at the two parts of this graph that tell us information, we can see that the thermodynamics of these reactions differ, but also the kinetics of these reactions differ, the height of that activation energy barrier. All right, we're just going to point out that this red curve here, which one's the faster reaction, blue or red? Blue, right? So this one's slower because of resonance and chloride mobility. All right, so we have these two different products that we could form here. Again, we said that we have temperature that will give us one versus the other. All right. We have what we call our well, let's do the other one first. We have what we call our kinetic product. Your kinetic product is the one that forms the fastest. Due to smaller activation energy. All right, I'm going to add to this a little bit, so I'm going to leave some room. Our other product is what we call our thermodynamic product. This is the one that is more stable due to lower product energy. All right. So your kinetic product is the one that forms the fastest. Your thermodynamic product is the one that's the more stable. Your kinetic product is what will form at low temperatures. All right, let's go back to this graph here and imagine that our reactants, our HCl, and our conjugated diene here is that little marble. And it needs to jump from the reactant side to the product side. Well, if it's at low temperatures, that means that this little marble here does not have a lot of energy. It is moving very, very slowly on this little curve here. And the only thing it's going to ever be able to do is jump over the smaller activation energy barrier. It doesn't have a lot of energy because we're at low temperatures, so it can only muster jumping over that small barrier there. Not only there, but once it does, it's stuck. Right? There's definitely no way that it's going to be able to jump back over that much larger barrier to go in the reverse direction. Okay? So our kinetic product is the one that forms fastest, and that will occur at low temperatures because our little marble here doesn't have very much energy to jump over anything at all. Our thermodynamic product, this is the one that will form at high temperatures. It'll form at high temperatures because now we've got a lot of thermal energy. Our marble can jump over anything it wants here, right? So it can make it over that larger activation energy barrier to get to the 1,4 adduct, no problem. And even if it does jump over this 1,2 barrier here, it can go back the other direction. And it's going to go back and forth until it settles at the lowest possible energy state, which according to this diagram here is our 1,4 adduct. All right, so at high temperatures, we get our thermodynamic product, whichever one is the more stable or lower free energy on the product side. Okay, our kinetic product, as was in this example here, it's always going to be that 1,2 adduct. All right, so our kinetic product, we can say always that 1,2 adduct. Because there's no resonance required and the proximity of that chloride ion. All right, so your kinetic product, the one with the lower activation energy barrier, our blue curve here for our 1,2 adduct, that's going to be the one that forms at lower temperatures. I will just note that because we had a symmetric diene here, there was only one possible 1,2 adduct that we could have. All right, if we have an asymmetric diene, we have to be a little bit more careful. Again, it's going to be one of those 1,2s, but either one of our double bonds could react to form a 1,2 adduct. And the other thing that's going to influence the height of that activation energy barrier is the stability of that carbocation intermediate. So we're going to note here, all right, if it's an asymmetric diene, our major product has the more stable, i.e. more substituted allylic carbocation intermediate. Allylic carbocation intermediate. All right. So, kinetic product, this is the one that forms the fastest. This was the one that will be major product at low temperatures. It's always going to be one of your 1,2 adducts because there's no resonance involved and the proximity of that chloride ion does not require a lot of thermal energy. If it's an asymmetric diene, though, you're going to have to draw both of your 1,2 carbocations to figure out which one's going to be the most stable. Our thermodynamic products, this is the one that forms at higher energy. And in our example up here, it was that 1,4 adduct, but we got to be careful, that's not always the case. In this case it was, because that was our more substituted double bond, but we can think of alkenes where that wouldn't be the case. So we have to say for this one it could be either the 1,2 or the 1,4, whichever is more stable or has that more substituted double bond. Okay, so in this case, in our first example that we did here, it was indeed that 1,4 adduct, but you can't just always say it's going to be the 1,4 adduct. You have to draw all your possible products and look to see which one is going to be the most stable, aka which one has that more substituted double bond. All right, and again, we can just note, in this case, there was only one 1,2, and 1, 1, 4, but we're going to say if it's asymmetric, we got to draw all 4 possible products to determine which one is most stable. All right, so electrophilic addition of conjugated dienes here. We got 2 possible things that could happen. We could either have a 1,4 adduct form, which is our normal product that we would expect just based on analogy of what we learned about alkenes. But then we also have this 1,4 product that can form as a result of resonance here. All right? And what's going to be the major product at low temperatures versus high temperatures depends on this kinetics versus thermodynamics business. Our kinetic product will form at low temperatures. Our thermodynamic product will form at high temperatures. All right, so let's try to do one that's a little bit more difficult. We'll use an asymmetric diene here. Right, so first thing I could ask you, what is the major product at low temperatures? All right. Because we have an asymmetric diene here, we know it's going to be one or both of our 1, 2 adducts. All right, but we got to look for the most stable carbocation. All right, so I want you to try to give me your 2 possible carbocation intermediates. The first would be if this first double bond reacted, the one between carbons 1 and 2, and the second would be if that other double bond reacted, the ones between carbon 3 and 4. All right, so we had that first double bond between carbons 1 and 2 react. The hydrogen would go on carbon 1, that carbocation on carbon 2. If we had our other double bond react, my hydrogen would go on carbon 4, and my carbocation on carbon 3. Okay? Both of these, if our chloride ion reacts, would be our 1,2 adduct. but one of these carbocations is more stable than the other. All right? What do we think? The one on top or the one on bottom? Which one's going to be the more stable one? The bottom one. So they're both allylic, right? Importantly, you'll always get an allylic carbocation, but not only is this one allylic, it's also a tertiary allylic carbocation. So in this case, my major product would be the one that forms on that carbocation there. Get our methyl chloride. This one would be my major product at low temperatures. All right, we'll probably get a little of this one too, but it wouldn't be our major product. Right, so since we're at low temperatures, I know it's going to be one of those 1,2 adducts, but it's going to be the one that has that lowest possible activation energy barrier, and this carbocation that's more stable will lower that activation energy barrier, meaning this will be my major product at low temperatures. All right, so lastly, what I could ask you is now the flip. What's the major product at high temperatures? And for this, we're going to have to draw all 4 possible products. All right, so how do we get 4 possible products? Because we have 2 1,2s and 2 1,4 adducts. And determine which one is the most stable. All right, and by most stable, what is it that I'm looking for? More substituted double bond. Yep. Cool. All right, I'm going to have you all do that one at home. You're going to come in with those 4 products drawn, and we'll finish this up next time. We'll start next time with it.